Alright, so use Green's theorem to work out this problem. That's the first part. Alright, what'd y'all get? I do everything for y'all. R to the fourth over 4, 0 to 2. That's just going to be 4, right? 16 divided by 4. 4 d theta. Alright, it's not too bad. Let's see if I can find us one more problem, maybe using Green's theorem to find some work. Put it to work for us. I think you'll need to do another line integral, or you want to do a work one? Maybe one more line integral? Alright, let me find an even one that way. Alright, so here's an even problem. Because I know that y'all like to work these odd problems. Maybe on the next test I'll just put all odd problems in the back of the section on it, just to see how many of you have worked them. But just because I said that, I probably won't do it. Or will I? Alright, so remember, find your m, find your n, then take your derivative of your m with respect to y, your n with respect to x. Bless you. All right, so whenever you set up your double integral, you got the double integral of what? So this is why I need Jaden in here, because he would answer. Very good. So you got 2y minus negative 2y, right? I know, because I haven't unfrozen the screen. Sorry. Just didn't want to show you all of my cool work. All right. So now I need to just set up my integrals. Have my path there. So that's, again, 4y. If you didn't get that right, I will say a brief prayer for you after class. The dA is r dr d theta. And we have 4y. So what is y equal to? R sine theta. So we're going to have 4 and then r sine theta times r dr d theta. So that's going to be 4r squared sine theta dr d theta. What are my boundaries for r? Look, r equals 1 plus cosine theta. So 0 to 1 plus cosine theta. Let's see. Okay, and then our boundaries for theta, 0 to 2 pi. Do you remember what the path, what would 1 plus cosine theta look like? I'm just curious about this path since it's not given to us. Know if it was just cosine theta what it would look like, but it's 1 plus cosine theta. Wonder if that's just going to shift it up. This is polar. 1 plus cosine theta. So we're traveling around that entire thing there. So that's why we have to go 0 to 2 pi. There, all the way around the heart, or the Pac-Man, or whatever you want it to be, the cardioid. All right, so first, integrate with respect to r. I have a 4 up there I can bring out, and then when I add 1 to the power, it's going to be r cubed. Then I got to divide by 3, right? So I'm going to go ahead and bring the 3 out as well. And then I have to evaluate r cubed from this top boundary to the bottom boundary. The bottom boundary gives me a 0. So it's going to be sine theta times 1 plus cosine theta cubed. d theta. What's the easiest way to do this integral? It's actually super easy. It's not complex at all. The u is going to be what's being raised to a power. So then the du is equal to what? 0 minus sine theta. And your sine theta is on the outside. So this is just a u substitution integral. Because that inside just becomes u to the third because your du is present. You do have to bring a negative out. Let's be negative 4/3. And then that's the integral of u to the third du d theta. All right, so what's that going to be? It's going to be u to the fourth over 4. And u is 1 plus cosine theta. So if it's u to the, we got that negative 4/3 integral here to here. U to the fourth is 1 plus cosine theta to the fourth over 4. This and this are going to cancel out then. I don't know. I got to evaluate it. 0 to 2 pi. Alright, so that's a negative 1/3 times. I'm going to plug in a 2 pi. So that's 1 plus cosine 2 pi minus 1 plus cosine 0. Those are both raised to the fourth as well. So cosine of 2 pi is 1, cosine of 0 is 1, 2 to the fourth is 16, 16 minus 16. All that's just going to equal 0. It was a line integral, and we started and stopped right there at the same point, so it was equal to 0. Alright, let's do one quick one with work. Let's see. Let's do another polar one. Those are the easiest, I guess. Alright, so we have a force. We have a path. Let's assume that a particle is traveling counterclockwise around the closed path. And let's calculate the work. Alright, so here's where, what are we actually doing? We're doing a line integral of e to the x minus 3y dx plus e to the y plus 6x dy. So if we apply Green's theorem, then what would that be? Let's see. Integral of m with respect to y is -3, and the integral of n with respect to x is 6. This would be the double integral over the region of 6 minus -3 dA. So what is R2 cosine theta? It's a circle. Do y'all remember? Cosine theta. Notice what the radius of this circle is. It's 2 all the way across, but the radius is 1, right? It's 2 all the way across because when you plug in a 0 right here for an angle measure of 0, you would get 2 times 1. So that's why the intersection point is 2 here. Alright. So that's going to be 9 r dr d theta. We've already established the point that the radius is 1. Now, to trace out the rest of this circle, though, do we have to go from 0 to 2 pi, or do we go from 0 to pi? I'm trying to pull up a table so we could look. Let's see if this works. That's a circle, even though it doesn't look like one. If you don't, I mean, it's kind of hard to visualize these as well, like -11 for theta, because that's in radians. So remember, -6.28, that would be 2 pi. So when you're back around here, you can see it's -6, it's that, but -6.28 would be 2. So we would need, let's see. So negative pi would be somewhere around in there. So to get to negative pi, negative 3.14, that would be, this is the pi right here. So negative 3.14 would be really close to -2. So I think we need all the values to trace out the entire polar graph. That's what I'm getting at. Alright. Which would mean that we need to go from 0 to 2 pi. So if I integrate, that's 9r squared over 2. And then you evaluate that 0 to 1. So that's going to be 9 halves. So you have 9 halves theta evaluated from 0 to 2 pi. Gives you what? 9 pi. So that's the amount of work that's done. It'd be 18 pi over 2, or 9 pi. So the last part of this section is on the alternate forms of Green's theorem. Let me make sure that I covered everything about Green's theorem that I wanted to cover. I did not. Just one quick thing. Green's theorem and conservative vector fields. If you haven't noticed, we've been for all these closed line integrals we've done with Green's theorem, we've gotten an answer of 0. And so that is going to happen if your vector field, if you have a conservative vector field and it's closed, then the line integral is going to be equal to 0. So conservative vector field, and if C is closed, then your line integral using Green's theorem is going to be equal to 0. It doesn't have to be conservative. I mean, you don't have to have conservative vector fields. Alright, let's just look at now the alternate form real quick of Green's theorem. We went over what the curl of a vector field is. That was back in 15.1. I don't remember it, or I don't know if you remember, but the curl of a vector field F was equal to del cross with F. So to find that, you have to do this 3x3 determinant. And then I think this one was see, if we're in a plane, this is in the plane, you'd have 0k. You could just put 0 instead of 0k, or you can put 0k, I don't care. Anyway, the way that we have to work that, I just gave you the formula. I didn't actually make you go through and figure it out. But for this one, for 0k, we would find, that's how we would find it. So what that means is that Green's theorem, that's this. You know, once we apply Green's theorem, we have this here. This second part right here, this is Green's theorem. It's actually equal to, if we do have certain conditions, we do have, this is equal to the double integral over the region of the curl of f dotted with k dA. This is the first alternate form. Extensions of this form actually produce Stokes' theorem that we're going to cover in section 8. So Green's theorem and Stokes' theorem are related. The second alternative form goes, instead of the curl, we look at the divergence. So here's the second alternative form. And it says the line integral of f, the dot product of f dotted with n ds is equal to the double integral over the region of the divergence of f dA. And that's the second alternative form. And this alternative form is called divergence theorem. So the first is going to relate to Stokes' theorem. And that's 15.8. This alternative form of Green's theorem is going to relate to the divergence theorem, which is 15.7. So we'll work more with these in those sections. But from Green's theorem came these two, this Stokes' theorem and divergence theorem, which are like the last two topics that are generally covered in Cal 4. All right. And that's it for today.